Stoichiometry is a multi-step process in order to solve chemistry equations. This is really one of my favorite parts of chemistry because it really forces you to think through a situation. And that's the real challenge, is taking everything we've known up to this point and forcing us to apply it. So we do need to know how to balance equations. We've done that. We've done mole conversions. And really that's primarily what we'll do. But since the beginning of the year, I've been telling you we're going to try to cancel units we don't want, keep the units we do. And it really is all coming together now for stoichiometry. Here's an example. Now, mole problems are where you're given a mole value. I don't think they're particularly useful because there's never any situation where you actually be measuring moles of any substance, because we would have to count 6.02 times 10 to the 23rd formula units or atoms or molecules, and that's just way too much to accomplish in even many years of counting. We would not be able to get to that amount. So I prefer grams or volume, just so you know, for a test, but these are sometimes on like a chemistry Olympiad or an AP or a chemistry SAT2. So you will see them, but I just really have a kind of a bias against them because we're not really doing all the steps of stoichiometry, and you really wouldn't deal with a situation where you have 2.5 moles of calcium carbonate, for example, in this problem. But here we have calcium carbonate reacts with hydrochloric acid to produce calcium chloride, water, and carbon dioxide. How many moles of acid are required to react with 2.50 moles of calcium carbonate? Now, be aware here, we're making water. We have a bubbling gas coming off. And calcium carbonate is basically the same material that is made in many mollusks, clams, snails. That's their shell. Limestone is also when marine animals die and their shells settle to the bottom of the ocean, then that turns into limestone. That's calcium carbonate, just so you're aware of what that actual compound is. Insoluble in water, we know most carbonates are not soluble in water. However, when we have acid in the ocean, for example, the carbon dioxide that's going into the ocean right now is becoming carbonic acid. It does actually make calcium carbonate more soluble. So we know in this particular problem we have calcium carbonate because it says it. We need to know what calcium and carbonate are. We need to know that carbonate has a -2 charge. Calcium has a +1 charge. So the formula unit would be CaCO3. We know it's a solid in water. We have hydrochloric acid. We know since it says hydrochloric acid, it's aqueous solution of hydrogen chloride. We need to know that by now. It will produce calcium chloride. Calcium has a +2 charge. Chloride, each one has a -1 charge. Therefore, we need 2 -1s to balance the +2. We get water, which again, we're going to see hydrogens from here joining with oxygens from here to make water, and then carbon dioxide. Now, this is not tremendously hard to balance, but what I can see is I have 2 chlorides here. I would need 2 chlorides over here. If I have 2 chlorides here, and I have 2 hydrogens, because it's going to be 2 formula units of HCl, then I would have my 2 chlorides over here. I would have my 2 hydrogens over here, 3 oxygens, 1, 2, 3 oxygens, 1 carbon, 1 carbon, 1 calcium, 1 calcium. I'm balanced. So it's 1 calcium carbonate, 1 mole of calcium carbonate, 1 formula unit of calcium carbonate, 2 moles or 2 formula units of hydrochloric acid makes calcium chloride, water, and carbon dioxide gas. That is your step 1, to balance the equation. And I really think that's very important for setting up any stoichiometry problems, to know how to balance an equation. Step 2 is not necessary in this case. We do not need to change any units to moles because we're given moles already. Step 3 is the mole ratio. As I discussed, this is a fairly simple ratio. Step 4 will be to find, if I have 2.5 moles of calcium carbonate, how many moles of hydrochloric acid would I need? If I set it up as a cross multiplication, I keep my mole ratio as a reference for how many moles of calcium carbonate I will need. Understand that at no point do I need to do anything beyond have my mole ratio and the amount that I have. And once I do my cross multiplication, I'm going to get the answer that I need. I'm going to get exactly how many moles of hydrochloric acid I would need. Now, you may notice this is a 1:2 ratio. So I would predict that the number of moles of hydrochloric acid would be double the moles of calcium carbonate. And in that case, we find out that's true. If I do my cross multiplication, I find that out. I can set this up another way. It's the way we've been setting up things all throughout the year. I have 2.50 moles of calcium carbonate. For every 1 mole of calcium carbonate, I need 2 moles of hydrochloric acid, according to the equation. Therefore, if I put 1 mole of calcium carbonate on the bottom, I cancel those units out. I'm left with 2.5 moles times 2 of hydrochloric acid, and I get the same answer. Just so you're aware, there's 2 ways of solving this. I primarily teach this way. However, Dr. Carell does this way. They're both equally useful and equally acceptable. Step 5 in this case is not necessary. We have our answer already, because it's how many moles of acid are required to react with 2.5 moles of calcium carbonate. Well, the answer is 5 moles of hydrochloric acid. There's something else I need to animate, but here's a mass problem. I think these are much more useful because we can actually measure mass with a scale. So given the equation, carbon monoxide plus oxygen produces carbon dioxide, how many grams of carbon monoxide are required to make 55 grams of carbon dioxide? You need to keep track first. What is your carbon monoxide? What is your oxygen gas? And what is your carbon dioxide? So the question is asking, it's not even focused on the oxygen here. It's asking how many grams of carbon monoxide do you need to make 55 grams of carbon dioxide? Now you'll notice carbon dioxide here is a product. In our previous situation, we were dealing with the amount of a reactant to find the product, but the process is exactly the same. You're given a unit. So first, balance the equation. If I put 1 carbon monoxide here and 1 carbon dioxide here, I would need 1 atom of oxygen. Unfortunately, in nature, oxygen does not exist as single atoms. It exists as molecules. So I'm going to need 2 carbon monoxides. Each of those 2 carbon monoxides to get 1 of the atoms from an oxygen molecule in order to become 2 carbon dioxides. That's my balanced equation. Now, it says I'm given how many grams of how many grams of carbon monoxide are required, but I'm given 55 grams of carbon dioxide. So my next step will be to change grams to moles, 55 grams of carbon dioxide, because that's what I'm given, times 1 mole over the gram molar mass of carbon dioxide, because it's 12 plus 16 plus 16, or 44. That gives me 1.25 moles of carbon dioxide that I'm producing. I need to know how much carbon monoxide has to go in. So I find my mole ratio. 2 carbon monoxides to 1 oxygen to 2 carbon dioxides. From there, I can set up my cross multiplication. So on this side is the ratio, and on this side is my actual scenario, how many moles of carbon monoxide when I need to produce that much carbon dioxide. And the mole ratio is what's going to get me to what I need. Now, if I cross multiply this, you can see it's 2x equals 2 times 1.25, which means I get 2 times 1.25 divided by 2, which means it's 1.25 moles of carbon monoxide. It's a lot more complicated than what you actually need to do. I could set it up this way as well. 1.25 moles of carbon dioxide. I have my mole ratio because I want to find moles of carbon monoxide. So I'm going to have 2 moles of carbon monoxide over 2 moles of carbon dioxide, because that's what the mole ratio tells me. I'm going to cancel out my units of moles of carbon dioxide. I'm going to be left only with moles of carbon monoxide. I get 1.25 moles of carbon monoxide. But I'm not done, because this question is asking how many grams of carbon monoxide, not how many moles. So my last step will be to turn my moles of carbon monoxide into grams of carbon monoxide. I do that by multiplying by the gram molar mass of carbon monoxide, which is 12 for carbon plus 16 for oxygen, gives me 28 grams. 1.25 moles of carbon monoxide times 28 grams gives me 5 grams of carbon monoxide. And that is exactly what the question is asking me to solve. Some more things I need to animate. Now, I chose this particular problem because this is a particularly nasty problem. In this particular case, phosphorus is written as phosphorus 5 oxide. Now, that is one way it can be written, just so you're aware of it. That means that phosphorus has a +5 oxidation number, +5 charge, more or less, on the atom. Oxides are -2. This is not a peroxide at -1. It's an oxide with a -2. Another thing is phosphorus in nature occurs as a 4-atom molecule. So we're going to have to take that into consideration. But what you need to know as far as the name phosphorus 5 oxide is that each phosphorus is going to have a +5 oxidation number, basically the same thing as a charge. So if one phosphorus has 5 and each oxide has a -2, I'm going to need 2 phosphorus and 5 oxides to make the molecule. Therefore, I have P4, which is my phosphorus in its normal state, plus oxygen gas is giving me this molecule. 5 oxides have an overall -10 charge because each oxide is -2. These phosphorus have a +5 charge. I need 2 +5s to make a +10 to cancel out a -10 from the oxygens. That's the simplest way I can make this molecule. Okay, so I'm given 50 grams of phosphorus. I need to find how many grams of phosphorus 5 oxide should be produced. First thing I need to do is have a balanced equation. This is not a balanced equation. I'm going to need to have my phosphorus. If I notice in my original, when I wrote it out originally, I had 4 phosphorus here, 2 oxygens, but I need to have 2 phosphorus and 5 oxygens minimum. I don't have anywhere close to that. Since oxygen occurs as an O2, I can never get an odd number out of this molecule. So actually this will have to be a multiple of 2 in order to make this all work. The simplest way I can do that, I have P4. If I have P4 and I have P2O5, I'm going to need at least 2 P2O5s on the product side. That way I have 4 phosphorus atoms on the reactant side. I have 4 phosphorus atoms on the product side. If I have 2 molecules of phosphorus 5 oxide, or what I would call diphosphorus pentoxide, if I have 2 of those, I actually have 10 atoms of oxygen. So if I have 10 atoms of oxygen, just because I need to accommodate these 4 phosphorus atoms, I have 4 phosphorus atoms. Now I have 10 oxygen atoms. The nice thing about having 10 oxygen atoms is that that's the same number as 5 oxygen molecules, which makes my life a lot easier. So now I have 10 oxygen atoms, 4 phosphorus, I'm good. My step 2 is to take those grams of phosphorus and turn them into moles. Now notice, just like O2, instead of being 16 grams, is 32 grams, P4, instead of being 31 grams, is 124 grams. So I'd have 50 grams of P4, because that is in my equation. 50 grams of P4 times 1 mole over the gram molar mass of the phosphorus molecule, not the phosphorus atom. That gives me 0.403 moles of phosphorus molecules. Now again, why do I need to do it this way? Because that's what I have in my formula. Keep it consistent. Whatever you have in your formula, keep it consistent with all of your other calculations. My ratio is going to be phosphorus, 1 phosphorus to 5 oxygens to 2 diphosphorus pentoxides or phosphorus 5 oxides. Now I have my mole ratio for cross multiplication. 1 mole of phosphorus to 2 moles of diphosphorus pentoxide phosphorus 5-oxide. Why? Because that's what it's asking for. If I have phosphorus on the top, I keep it on top. If I have phosphorus, diphosphorus pentoxide or phosphorus 5-oxide on the bottom, I keep my unknown value on the bottom as well. With the cross multiplication, I get that X equals 2 times 0.403 or 0.086 moles of diphosphorus pentoxide. The other way I can do it is I know how many moles of phosphorus molecules I have. How many moles of phosphorus molecules I have. And then I multiply that by the ratio where I have what I want on the top, what I want to get rid of on the bottom. These two units cancel out, and I get 0.403 times 2, which is 0.806 moles of my substance, my phosphorus 5 pentoxide or my diphosphorus pentoxide. Step 5, it does ask for grams. So I need to multiply the moles of this that I have by the gram molar mass so that my moles cancel out and I get the grams, and I get 114 grams of diphosphorus pentoxide or phosphorus 5-oxide. Now, why am I using 3 significant digits? Because my original problem was given in 3 significant digits. Okay, now, this is where we're given a certain number and we're needing to consider mass. Again, the steps are exactly the same for all of these. So how many milliliters of liquid water can be produced from the combustion of hydrogen with 9.03 times 10 to the 23rd molecules of oxygen? What I need to focus on is what I'm given. I'm given 9.03 times 10 to the 23rd molecules. That's all I need to worry about to start. And the equation that gets me there. I have hydrogen as a gas. I have oxygen as a gas. Now, this is described as a combustion reaction. Anytime you're burning anything is technically a combustion reaction, even though the products of most combustion are carbon dioxide and water. In this case, you do have water as our product. But the only way you can get only water as a product is if you burn hydrogen. So that's why this is from Dr. Carell's notes. So he would call this combustion. It's the same thing as a synthesis reaction. Just the fact that you're taking hydrogen, you're burning it with oxygen is why you're making water. That's acceptable as well to call it combustion. Now, step 1 is to balance this reaction. I have 2 hydrogens here. I have 1 oxygen. I have 2 oxygens here. So minimum, I would need 2 molecules of water over here. If I have 2 molecules of water, now I have 4 hydrogens. And the only way I can get 4 hydrogens on the left is to make 2 hydrogen molecules. So 2 hydrogen molecules plus 1 oxygen molecule makes 2 water molecules. The reason why these have to be O2s, as you've seen before, is because they're diatomic in nature. So now I take my number of molecules that I'm given, and I'm converting it to moles by numbers, not by gram molar mass. I see too many people jumping to gram molar mass when there's no way you could do that. You're going to get moles over grams. That doesn't make any sense. What's going to make sense is this is your number of molecules. This is the number for a mole. So you're going to have to get your 1 mole over your number of units, These numbers of units will cancel out, and I end up with 1.50 moles of oxygen. If I had moles over grams or something like that, I did something wrong. You've got to be clear. This is a number problem because it's giving me a number of molecules. Therefore, my conversion is moles and 6.02 times 10 to the 23rd numbers of particles. Once I have this, it makes life a whole lot easier because I can find my mole ratio, 2 hydrogens to 1 oxygen to 2 waters. And then I can either cross-multiply. Again, this is set up my mole ratio. I want to find water. I know oxygen. If water's on the top, water needs to stay on the top. This is my unknown amount of water that I need in moles. And this is my known amount of oxygen that I have. From there, I'm going to solve for x. So in this case, x equals 2 times 1.50, which is the same as 3 moles of H2O. Now, should I put 3.00? Yeah, to be really consistent, I should, just to make sure, because I'm going to get 3 significant figures in my final answer. Should I be consistent? Yes. I just was running out of space on this slide. Now, the other way of doing it, I'm canceling out my units given. I want to find units requested, right? I want to find how much water can be produced. First, I'm going to go with moles of water. So if I set it up in this way, for every 2 moles of water that's produced, I use 1 mole of oxygen. I have 1.5 moles of oxygen. The moles of oxygen will cancel out if I set it up this way, and I get 1.5 times 2 moles of water. I get 3 moles of water. Now, I don't have a conversion of moles to milliliters, but I do have a conversion of moles to grams. Stick with that. 3 moles of water times 18 grams, because it's H2O, which is 16. 2 hydrogens, 2 times 1 plus 16 is H2O over 1 mole of water. That way my moles of water cancel out. 3 times 18 is 54 grams of water. Now, if I know the density of water, which is a given, it's pretty well established what a gram of water is. The density of water is 1 gram per milliliter. If this were something like mercury, I'd probably have to give you the density of mercury in order to be able to figure this out. But what we're doing, density is 1 equals mass over volume. Now you just need to solve for volume. You get the volume as 54.0 milliliters. Because in order to get a 1 here, you're going to have 54.0 divided by 54.0, which is 54.0 milliliters of water. That's your answer for this mass number problem. One other conversion we need to consider is liters of gas at STP, standard temperature and pressure, 273 Kelvin and approximately 1 atmosphere of pressure. So slightly less. It's 100 kilopascals, which we'll talk about when we get to gas laws. But 16.8 liters of chlorine gas at STP react with zinc in a synthesis, a combination reaction. How many formula units are produced? So what are we going to make with zinc and chlorine? We're going to have zinc. We're going to put together chlorine. Chlorine will be reduced. Chlorine will take electrons from zinc in this case. This is not a single replacement reaction. This is a reduction reaction. This is where ionic compounds form, and they form because one electronegative element will take electrons from a metal in this particular case. The only possible reaction here would be zinc and chlorine making zinc chloride. Zinc has a +2 charge. Each chlorine has a -2 charge, or a -1 charge. We have an overall -2 +2. That's my zinc chloride. This is a salt from a metal and a non-metal. Step 1 is to balance this. Thankfully, this one's already balanced. If it weren't balanced, you just go through the same steps we've done over and over in order to balance it. Step 2 is to take my units that are given, 16.8 liters of chlorine, and I will multiply that by 1 mole over my value for liters of the gas at STP. It's one of the things you should memorize by now. 22.4 liters of gas at STP is what 1 mole of any gas, the space that 1 mole of any gas occupies. My units cancel out. I get 16.8 divided by 22.4 moles, and that's 0.745 moles of chlorine gas. From there, I find my mole ratio, which is nice, 1 to 1 to 1. If I want to just do the process like I always do, I have my mole ratio here, 1 to 1. I have the moles that I have, keeping them at the top, keeping them consistent, and the moles I need to find, which means 1 to 1 ratio. When it's 0.75, it's going to be 0.75 moles of chlorine. I'm going to make 0.75 moles of zinc chloride. The other way of doing it, I know how many moles of chlorine I have. Then I multiply that by the units I want over the units I want to get rid of. My moles of chlorine cancel out. I get 0.75 moles of zinc chloride as the answer. Now, this is asking how many formula units are produced. It's not asking grams. It's asking a number. It's asking for a number. How many formula units, which is, again, the magic number here. 0.75 moles of zinc chloride times 1 mole of zinc chloride's on the bottom, so the moles cancel out. This is my number, 6.02 times 10 to the 23rd. This is how many formula units we have in a mole. This is how many atoms we have in a mole of an element. This is how, this is how many molecules we have in a mole of a compound as well. So be aware of that. 0.75 moles of zinc chloride times 6.02 times 10 to the 23rd for 1 mole. My moles will cancel out. I get 4.51 times 10 to the 23rd formula units of zinc chloride. And that is how I can go from volume to number. In every case, you're going balanced equation, units to your moles, mole ratio, cross multiply or eliminate what you don't want. And then you're going from moles to the units you requested. This is why I love these, because you really got to think your way through a problem. We will hopefully practice some more complex, difficult stoichiometry problems very soon.